Okay, so welcome everybody. My name is Bruno Julia from the University of Barcelona, from the Department of Quantum Physics and Astrophysics and the Institute of Cosmos Sciences. And we are very pleased to have today an online seminar from Professor Gabriele de Chiara from Queen's University in Belfast. So let me just give a brief intro about Gabriele. So Gabriele did his degree in 2002, this was in the University of Palermo, and then the PhD in 2005 supervised by Professor Rosario Fazio in the Scuola Normale Superiore. Then he was a postdoc in the University of Trento with Tommaso Calarco in the group of quantum optics at the Universitat Autònoma de Barcelona with Giovanna Morigi, and then a postdoc in the University Autònoma of Barcelona under the supervision of Anna Sampera. This was until 2011, and from 2011 he has been affiliated to Queen's University of Belfast, first as a lecturer and since 2020 as a reader. So he's a very well-known actor in the field. He's associate editor of Physical Review A, handling papers on quantum information, and his research is in statistical mechanics and thermodynamics in quantum regime, quantum information processing, condensed matter in long-dimensional system, entanglement and quantum info, density matrix renormalization group, and other tensor network methods, etc., etc. So thank you very much, Gabriele, and the floor is yours.
Thank you, Bruno. Thanks a lot. Welcome, everyone. Let me thank Bruno again for the very nice introduction and for inviting me to give this seminar. It's a pity I cannot be there in person. Okay, so today I'm going to talk about quantum thermodynamics and its relation with quantum computing. So this is the outline of the talk. So I'm going to start with some motivation and then introduce the so-called collision models, which will be the main characters of this talk, which will allow us to look at thermodynamics and its connection to quantum computing. I will then talk about quantum coherent paths, which is not the usual thing that one assumes in thermodynamics. And then in the second part, I will talk more about quantum computing, in particular adiabatic quantum computing, and how to accelerate quantum annealing with collision models. Okay, so let's start with the first part that will be on thermodynamics of collision models. So the motivation is to study open quantum systems that are very central to many areas in physics, for transport, complex systems, quantum technologies, and of course thermodynamics. So to model open quantum systems, normally one assumes that there is a system, which may be one atom or one cavity, or for example, a magnetic material in contact with an environment, usually assumed in equilibrium. And what one normally does is to assume a microscopic model, typically something like caldera-legged model, which is something like this, where the system is in contact with an ensemble of harmonic oscillators, spin boson models, or if you're looking at transport, you may model the environment as fermionic paths, which exchange particles with the system, or you can have more, maybe in solid state physics, you can have different models with spin stars. So your system is interacting with a network of spins rather than harmonic oscillators. So then, because these many-body problems are impossible to solve analytically, one resorts to approximations, and typically one goes into the so-called Born-Markov approximation. So weak coupling to the environment and no memory, Markov meaning no memory in the environment. And sometimes you can end up with a simple equation for the system, for the evolution of the system alone, which is called the Limdahl-Master equation. So this is the typical evolution that in open quantum system that governs the evolution of a dissipative system. And there is an alternative to this, which is the so-called collision model. Sometimes this is called repeated interactions, and here there are a few reviews and papers where you can read more about this, where the environment is modeled as a sequence of small units which interact for a short time with the system and then they are discarded. So they interact for a small time and then they fly away. And so the question is, okay, so then what can you simulate with these collision models? What can we reproduce with these models rather than using the traditional, spin boson models? And so suppose that we consider a master equation in Limblad form. So this is one of the most general evolutions that you can have for a dissipative quantum system. Can be local or global. This is like a technical detail, but this is just to say that this is very, very general. The environment can be a thermal environment, in equilibrium at temperature T, or it could be an out of equilibrium environment, for example, a squeezed environment. And the interaction of the system with environment can be individual, so one particle of the system interacting with part of the environment, or more collective operators interacting with the system. So anything goes. And it can be Markovian, or you can also describe certain classes on Markovianity. I'll come back to these later. Then, under these assumptions, we can simulate any Markovian Limblad master equation by using these collision models. So here, this is a cartoon of a system made of several subsystems. So this could be qubits, spins, harmonic oscillator, etc., etc. And we will see for each of these subsystems, you will need to have a collision model where auxiliary system prepared initially in equilibrium interacts with the part of the system, and then they fly away. And we need one of these sets of GANs with ancillas, with auxiliary systems for each of the baths that we have. So this is what we call the multipartite collision model. We describe this in this paper because we were motivated by reproducing dissipative evolution of quantum systems in quantum computers. This is a typical picture of a superconducting qubit, superconducting computer, which might be found somewhere here in the bottom, with all the refrigeration to achieve extremely low temperatures for the quantum computer to operate. So basically, here what we are saying is that we have a very general tool to simulate any possible dissipative model, or a very large class of dissipative models in quantum systems with this multipartite collision model. I just remember, if you have any question at any time, please feel free to raise your hand, shout. I can see Bruno, but if you have a question, he will tell me, and I will stop a moment. These collision models have already been implemented in a couple of experiments, one with photons in integrated circuits with integrated waveguides, where the different photons represent these ancillas that interact with the system and so on. The interaction is modeled by beam splitters. And the other platform where collision models have been implemented is indeed superconducting quantum computers with qubits, and there are a couple of papers where this has already been successfully realized. One very nice feature of collision models is the fact that they are consistent with thermodynamics. And this is regardless of certain assumptions with master equations. For example, if you consider a system which is only made of two oscillators, and each of them interact with a bus. So, for example, this one interacts with a cold bus, and this one interact with the hot bus. The way in which we can describe the thermodynamics is we can compute the heat flow from the system to each of the bus, the left one and the right one. And the heat flow is very simple to calculate because this is the energy change of the ancilla before and after the collision. So the ancilla comes in a thermal state, interact with the system, and then after the collision becomes out of equilibrium. If you compute the energy before and after the collision, that energy change is related to the heat flow into the bus. If you divide by tau, which is the time of the collision, you'll get the heat current into that bus. But then there is an additional ingredient, which is the fact that because to implement this collision, you need to switch on and off this interaction with the bus. In principle, because the Hamiltonian is time dependent, there will be a work term that depends on the time derivative of the total Hamiltonian itself. So this dissipative model will not only account for heat flows, but also for work production during the collision, which sometimes for dissipative models, this is not always the case. Normally, you only have heat flows and not current. But in this paper, this was a few years ago, we discovered that this external work is actually responsible for a prediction of heat flow from the cold bath to the hot bath. In this model that I'm showing here, is very simple to calculate analytically the steady state and all the heat flows. It's predicted that depending on the frequencies of the two harmonic oscillators, you can have heat flow from the cold to the hot bath. And this was kind of critique to the master equations. And we discovered that in reality, it's possible to have this anomalous heat flow because intrinsically there is a work term which was hidden before. They depended on the collision work produced after each collision. So let me go back to these multipartite collision models and their implementations on a quantum computer. And so I'm going to go a little bit more in detail. Suppose that we have a general Markovian Lindblad master equation. This is one of the most general evolutions that you can have for a quantum system, where, okay, this is the usual unitary term of the evolution of the system with its own Hamiltonian. And then here you have the so-called Lindblad jump operators that make the system undergo transitions from one state to the other. And this is the most general one where you can see the left jump operators and the right jump operators can be different. This is the most general one that you can have. And now, in order to implement this with collision models, for each of these pairs of operators NF DAGA, so this could be jump operators like ladder, like sigma plus, sigma minus, or A and A DAGA, which make the system do transitions from one state to the other. For each of these jump operators, I need to implement an interaction of the system, for example, here, qubit 1 and qubit 2, with an ancilla, with a flying ancilla P, in this way. So this is a kind of exchange interaction between the system and the ancilla. If we implement this Hamiltonian and then we make a gate, an evolution, a unitary evolution for a certain small time delta t, like this, we will be able to reproduce each one of these terms in the master equation. So the concatenation of all these gates for each time interval delta t will generate the master equation up to a certain time t, that is the evolution that you want to simulate. So in this way, this is a recipe to simulate any possible dissipative evolution of a quantum system. So let me talk a little bit more about the resources that are required to do this evolution and the analysis of the error that we commit every time we do this simulation, this approximation. So the global error is defined as the difference, is the norm of the difference between the exact evolution that you would like to simulate, okay, dissipative evolution. So this L is the Liouvillean of the evolution, and the actual concatenation of gates that I implement on the quantum computer, each of them with a time delta t, and I implement n of them. When I do this, I will get a sort of Suzuki-Trotter error that depends on the number of time steps that I do and depends on delta t squared. So in total, this will go like t squared as the total time that I want to simulate. So that's the global error due to the truncation, to the trotterization of the different gates, of the discretization of the time steps. And then in terms of the number of ancillas and the number of gates that are needed, using these results from an old paper in quantum computation, we can show that the number of ancillas, so the number of flying particles colliding with the system, grows only polynomially with the number of qubits in the system, the time that you want to simulate, and the error that you want to achieve. So if this is your tolerance, like 1% or 5%, the number of ancillas that are required only grows polynomially with these requirements, and so does the number of gates. So the number of gates also grows polynomially with these sizes. So the bottom line of this was the most important result of this paper, was that the quantum simulation of any Lindblad master equation is efficient because the resources that are needed only grow polynomially with the size of the system and the time evolution that you want to simulate. Okay, so let me come back a little bit to non-Markovianity. So I said that this model that I'm talking about is able to generate all possible Markovian master equation, but what about non-Markovian models where there is a memory in the environment? This sometimes occurs when the environment is not very large, like in a real system, in a quantum computer, or for example, if the interaction between the system and environment is strong, so that you have to go beyond the Born approximation. One way, there are different ways to deal with non-Markovian effects. One of these goes under the name of reaction coordinate method, or sometimes it is called as Markovian embedding. And the idea is to enlarge the system so that the new larger system is made of the original system S, which is your atom or your cavity, interacting with a small environment. So that's the new system. And now the environment, this auxiliary environment, interacts with the actual environment made of collision models. And the interaction between the collision models and the environment is Markovian. So this part is Markovian, but then the system, because it's embedded in this enlarged environment, has some non-Markovian effects because this small environment has some memory, has some finite time memory. And this is a way to simulate non-Markovian effects. The other way in which we can simulate non-Markovian effects is that, so the system now is the original system as before. The collision model is the same as before, but whenever an auxiliary qubit interacts with the system, before leaving, before being discarded, there is a chance with some probability P that is swapped with the next fresh unit that is arriving. So the system will have a chance with some probability to interact with the old ancilla that it has interacted before. It will interact with the same environment, and therefore the environment has some memory of the previous interaction that it did with the system. So, and this is another way in which you can simulate some non-Markovian effects. I'm saying you can simulate some non-Markovian effects because it's not clear whether you can simulate any possible non-Markovian evolution. This is an open problem. So it's guaranteed that you can simulate any Markovian model, but for non-Markovian models, you can simulate certain classes, okay? And there are many, many references. I'm not putting here all the references. I can give you some reviews on these if you want. Okay, any question at this stage? No? Okay, okay, good. So I'll move on and introduce a new ingredient, which is using coherent ancillas. So far we have used thermal ancillas. So the qubits that are interacting with the system are prepared in an initial equilibrium state at a certain temperature T. But suppose that instead we put just a little quantum coherence. So that means that there is a little bit of quantum superpositions between energy eigenstates. When the state was thermal, there was no coherence, there was no superposition of the energy eigenstates. Now we are going to add a little quantum coherence. And the way to model this is that we assume the state of the environment of each of these units to be the thermal state plus a small correction, okay, where epsilon is the strength of the coherence. Chi here, chi E, is an operator which is off diagonal in the energy basis of the units. So that means that there is coherence between the energy eigenstates of the ancillas, and square root of tau, here tau is the time of the collision. So that when tau goes to 0, to reproduce the master equation for very short times, the coherence that we put is infinitesimal. So it's really, really small. When we do this, we take the limit of tau going to 0. The collision model leads to the following master equation, where we have an extra term in the effective Hamiltonian of the system, proportional to this epsilon strength of the coherence, or magnitude of the coherence that we put. This d of rho s is the typical dissipative term in the mass equation. And G is proportional to chi, which is the off-diagonal part of the state of the ancilla, and V is the interaction between the system and environment. Okay, this simple modification has a huge consequence on the thermodynamics of the system. So first of all, the first law of thermodynamics is modified by this term. So if I look at the energy balance of the system as a function of time, we will see that this has two terms. One term which is new, you wouldn't have when the environment is thermal, and this we call this a coherent work term that depends on the coherence in the environment. And the second term is the incoherent heat. This is the typical thing that you will get for a dissipative, for an equilibrium environment. So the new term is this new coherent work that changes the energy balance of the system, the internal energy of the system. So that's the modified first law, but also the second law is modified. And we find, based on entropic considerations, that this coherent work is at least the loss in coherence in the environment. So as I said, these ancillas, they have initially some coherence before the collision with the system, and after the interaction with the system, they may have lost some of that coherence, which contributed to the energy balance of the system. Now, our modified second law says that this coherent work will be at least will be no smaller than the loss of coherence of the ancilla, and this is quantified by the so-called relative entropy of coherence. So this is basically the von Neumann entropy of the original state of the ancilla and its diagonal version when you completely decohere it. You put all the off-diagonal terms to zero. Okay, good. Now, having these coherent ancillas, okay, we got these fundamental results on the modified first and second law, but can we exploit these coherent ancillas? Is there a way to get an advantage, to turn these modifications into a thermodynamic advantage? And so to do that, we looked at thermal machines. So before looking at the case with coherence, I will look at the case without coherence. So again, we're going to take a step back and look at the case where the bath is made of ensemble of qubits with in thermal equilibrium at a temperature T1, and I'm looking at a qubit with an energy separation B1 between two of its levels. Then I have the system. The system is also considered to be a qubit with an energy separation B between the two levels, and a hot bath at temperature T2 larger than T1, again with an energy separation B2 between the two levels. So we implement the collision models, the train of cold ancillas of cold qubits interact with the systems. After the interaction, the state is slightly modified, and the qubits in the hot state also interact with the system, and then after the collision, the state is modified. As I said before, you can compute the heat flows from the system to the two environments, Q1 and Q2, and you will have some work production as well due to the collisions with the two baths. Okay, based on this, we can have different modes of operations. The system or the device can function as an oven, or sometimes this is called an accelerator. This is where the heat flows from the hot bath to the cold bath, and this is accelerated by external work. Yeah, and this happens, okay, depending on the ratios of the magnetic fields of the two baths. This may happen when this condition is fulfilled. So this is the normal flow of heat, the normal direction of heat flow, but it's accelerated by external work. You may have an engine. Instead, this is the typical textbook example where heat flows in the normal direction, so from the hot reservoir to the cold reservoir, but doing this, the system produces some external work that can be used for mechanical work, etc. And this happens when the ratio of the magnetic fields is between the ratio of the temperatures and 1. And then if you go in the other regime, you can have a refrigerator, which we kind of mentioned implicitly before, which is the case where heat flows from the cold bath to the hot bath, but this is only possible because there is external work done on the system during the collisions with the environment. And this happens when the ratio of the magnetic fields is smaller than the ratios of the temperatures. Okay, so these are the three possible modes of operations. I will talk about now their performance, and this is measured by the so-called efficiency. Again, if you kind of remember your undergraduate studies in thermodynamics, you remember that one can define, for example, for an engine, one can define the efficiency of the engine as the ratio of the total work done on the system, by the system, divided by the input heat from the hot reservoir. When you do this ratio for this particular model that I've talked about with qubits, the efficiency is given by a simple formula that depends only on the ratio of the magnetic fields. And this is known as the Otto efficiency for an engine operating with harmonic oscillators. For the other regime, where you have a refrigerator, so this is in the other regime of ratios of magnetic fields, one can compute what is called the coefficient of performance, COP, which is the ratio of, the quality figure here is the heat extracted from the fridge, so from the cold bath, divided by the work input that, this is the electricity, the energy electricity that you are putting into the refrigerator. So the ratio of these two will give you the coefficient of performance. Again, this only depends on the ratio of the magnetic fields, and these two values are known as the Otto values for the efficiency and coefficient of performance, because they are similar to what you would get in an ideal gas operating with a piston, with the compression, expansion, etc., etc. So mathematically, you have the same formula. So this is why we call them as the Otto efficiency. And notice that when the ratio of the magnetic field is exactly the ratio of the temperature, so this is the transition between engine and refrigerator, you get the Carnot limit. So the Carnot limit is the limit in which you transition from the engine to the refrigerator, but in that case, you get zero work and zero cooling. So this is a reversible limit. There is no irreversibility. There is no entropy production at this particular point. The engine or the refrigerator is reversible, and the device reaches the Carnot point. And that's the only point where the Carnot limit is reached, but this is the case where you get zero work and zero cooling. So in a sense, this is the most ideal thermal machine, but it's kind of useless because it doesn't produce any work, or it produces infinitesimal work. So instead, what we normally look at as a figure of merit is the efficiency at maximum power. So suppose that I want to draw a diagram of the output work for an engine, for example, as a function of its efficiency. And let me fix, if you want, the two temperatures, T1 and T2 of your environment. So if you have your car, this is fixed by the external environment and by the temperature reached inside the piston. So these are fixed by engineering. So can you optimize the other parameters like B1 and B2 of your device? And typically you get a curve that goes like this. So it's zero, the work is 0 in 2 points here and there, and then there is a maximum in between. This point here is the trivial point where B1 is equal to B2. And so there is no work done or performed by the system. The other point, which is maybe more interesting, is the Carnot point, where again the ratio of the temperatures is equal to the ratio of the magnetic fields. And again, here the work is 0, and the efficiency is the Carnot value, and this is the largest efficiency that you can obtain for a system operating with between thermal reservoirs at temperature T1 and T2. But there is a value in between, and that value is very important, because if you are designing your thermal machine, your car, for example, you would like to have the best power output, and you would like the efficiency at that maximum power to be very large. And now for a very large class of systems, this efficiency at maximum power is equal to the value discovered by Curson and Alborn, which is given by 1 minus the square root of the ratios of the temperature. So this is kind of reminiscent of the Carnot value, but with the square root. So therefore, this is strictly smaller than the Carnot value. And the other thing is that this is not universal. So it depends on the device that you have. If you have the ideal gas in a piston, in a harmonic trap, with the piston, etc., you will get the typical Coulson-Alborn. If you have a single qubit, you get the Coulson-Alborn. But there are some models that violate Coulson-Alborn, and you can also surpass the Coulson-Alborn limit, both for classical and quantum systems. Okay, so this was a little bit of introduction of the machines, of the thermal machines that we can create with collision models. Let me now add this extra ingredient of the coherence in one of the two baths. So what I'm going to assume is that I have a set of thermal ancillas, for example, the ancillas in the coupled to the hot reservoirs at temperature T2. And then I have a set of thermal coherent ancillas. So these are the ancillas in the cold bath. You can see that the arrow here is not pointing in the vertical direction. So for those of you that are familiar with the block vector is not on the z-axis, but is slightly at an angle, indicating that there is some initial coherence in the ancilla. So I'm using one bath of thermal ancillas and one bath of thermal coherent ancillas. What we see is that the efficiency of this engine or the refrigerator is still given by the Otto engine, but interestingly, you can surpass the Carnot value provided by T1 and T2, okay? So why is that? So I'm going to give you some details in a moment, but the reason is that we are using the coherence in the initial state of the ancillas as an extra fuel to provide more resources to the device. So this is a way in which we can exploit this initial coherence to achieve better performance. So here I'm claiming that we are surpassing Carnot, but of course we are using more resources to do that. So we are not violating the second law or anything. So, okay, so these are the results when I put some coherence in the cold bath. And this is a diagram where I have the amount of coherence in the cold bath and the field B1, okay? So if we go down here in the value for epsilon equal to 0, so this is the initial thermal state, okay? You can see that we have the three regimes. We have the refrigerator, the engine, and the accelerator exactly as before. And this is the Carnot point that I was talking about here that separates the refrigerator regime from the engine. And now you can see that when I increase epsilon, so that I put some coherence, above the engine, there is a new region, which I call R prime, where the system behaves as a refrigerator. But because this part is on the other side of the Carnot, in that region, the coefficient of performance at the refrigerator is larger than the Carnot value. And the reason is that the efficiency is always the Otto value, but the Otto value in this region is larger than the Carnot, because this is is a forbidden area if you didn't have coherence. If you didn't have coherence, you will be in the engine, not in a refrigerator. So this is a kind of forbidden region where you still find the refrigerator because of the coherence, and its efficiency is larger than the Carnot value.
Gabriele, one question.
Yes.
Yeah, the epsilon parameter, so the parameter quantifying the coherence, 0 means 0, that's clear, but 1 means what exactly? I mean, is large compared to what, or how are you actually measuring?
No, it's not like it's a dimensionless parameter. And if you remember, we are assuming, if I can go back. There we go. So it's still small, it's still infinitesimal, because we are treating square root of tau. This is multiplied by square root of tau, and tau is going to, we take the limit of tau going to 0. So epsilon is small, epsilon equals to 1 is still small.
Okay.
Okay. Good. Let me see if I can go. Any other question at this stage?
Can I have a question?
Yes, please.
So your system is the qubit, 3 qubits, right?
Yes.
Your system of interest is qubit, and 2 bus is the 2 qubits. do you need a collisional model? Can't you solve it exactly?
Yes, I can solve it exactly. Yes, but yes.
I thought, yeah. Sorry,
No, we can solve
this.
this. So all the results are analytical. So if you look in the paper, we have all the expressions for the heat flow to the cold baths and to the hot baths and the work. So everything is analytical there. All, even, for example, this line here, we have an analytical expression for this line. So everything is analytical, yes. If this is the question, right?
Yes, yeah. So you introduced collisional model, right? You solve the collisional model for this instead of solving, as I say, Schrödinger equation or von Neumann equation, right?
I'm not sure I get the point.
I thought the collisional model is still, ignore some effect. But my question was, like master equation, for sure you ignore some, information, right? For
we are not ignoring anything here.
Okay,
yeah.
okay.
Here we are not ignoring anything. I have control over everything in the system. We are not putting any dirt under the rug. We are putting all the things. We have the balance of everything. So we are not hiding anything here.
Okay,
That's the beauty of the collision models, I think.
Okay.
Okay, maybe I'll suggest to postpone this because I think maybe this is more philosophical, or maybe we can postpone the discussion until later. Okay, good. Sorry. Okay, good. So let me come back to this. So I told you that there is this refrigerator, special refrigerator regime where the efficiency is larger than the Carnot value. There is another region that appears above the accelerator. So without coherence in the bath, you have the accelerator. The accelerator is the trivial regime in which you heat the cold bath. Above that, there is a new regime, which is called the hybrid refrigerator. Now, the hybrid refrigerator is something of a magic system because it's a device that takes heat from the cold bath, put it in the hot bath, and at the same time, it produces some external work. It's an engine and a refrigerator. So obviously, with thermal baths, you will never have this. Okay, so this is only possible because we are consuming the coherence from the cold bath as a fuel to do two things at the same time: refrigerate and work production. So we have two effects from the presence of the coherence. One is that we surpass Carnot, and the second is that we produce the hybrid refrigerator. Similarly, when we put coherence in the hot bath, we have, again, similar regimes. We have accelerator, engine, and refrigerator. And again, this is Carnot. And we can have an engine in the region in which, without coherence, you will have a refrigerator. And as you can guess, the efficiency in this forbidden area here, where you have an engine instead of a refrigerator classically, in that region, we have that the auto efficiency surpasses the Carnot value for this particular engine. In this configuration, when coherence is in the hot bath, there is no hybrid refrigerator. So hybrid refrigerator is only in the case when coherence is in the cold bath. And we looked also at the efficiency at maximum power. So in absence of coherence, this is the result. So this is the work power against the efficiency. So here we have the result that I sketched before. This is the Carnot value. This is the maximum efficiency that you will get with thermal baths. And this is the Coulson-Alborn value. This is the efficiency at maximum power that you can have. And when you put coherence, there are two things that happen. First is that we go beyond Carnot, as I said, and we can look at an effective Carnot bound given the resources we have. So this is kind of, again, related to our modified second law. We have an effective Carnot bound. I have to say that the formula is not very nice, because it depends on epsilon, is very long. It's not as nice as the Carnot value, but nevertheless is the bound that we obtain for this case. And then the other thing that happens is that the efficiency at maximum power is larger than the Coulson-Albor. So we surpass both the Coulson-Albor limit and the Carnot limit. Okay, so I'm going to skip that and summarize briefly what I said in this first part for the collision models that allow the simulation of a large class of open quantum systems in a consistent thermodynamic way. And any limited mass equation can be efficiently simulated on a quantum computer. And I also show you how to enhance thermal machines with internal coherence, with coherence in the bus. Yes. I skipped this part on correlated bus because I think I don't have much time left. But I'd like to go to the second part. If there are no urgent questions, maybe I'll move on.
Can I ask another question?
Yes, please.
So you consider, qubit system for, to calculate efficiency and the work. Can you do same thing higher dimensional systems like qubit or no?
Yeah, so we have done some calculations for that particular system for D-level systems, but without coherence.
Mm-hmm.
And with D-level systems, this is quite interesting. We saw that, okay, you cannot surpass Carnot because you are using thermal baths,
mm-hmm.
but you can surpass the Coulson-Albor limit with D-level systems. And yeah, so I can give you the reference later if you want. But we didn't look at the case of D-level systems with coherence yet. My postdoc and I were now working on a 3-level system where that interacts with 3 baths at temperature T1, T2, T3, and one of the baths has coherence. So we are looking at this right now. We are writing a paper, so it will be out soon. Yes.
Because what depends on what kind of the coherence, probably how the how do I say coherence improve the efficiency or performance, but if there are higher level systems, depend on what kind of coherence, machine, how it's different, how the performance gonna be, I think.
Yeah, yes, I agree.
Okay, thank you.
Okay, cool. So in the last maybe 10 minutes or so or less that I have, I will talk about quantum optimization, in particular how we can accelerate certain tasks in quantum optimization using or being inspired by thermodynamics. So let me move to quantum computation a little bit. And you may know already that quantum computation usually works in the so-called gate model, where you have a bunch of qubits. You put some gates, and then after these gates, this could be unitary gates, etc., or measurements, etc., you get a final answer, and this is the result of your computation. This is, for the experts, this is the quantum teleportation circuit, just as an example. But there is an alternative model, which is called adiabatic quantum computation, that works like this. Suppose that I have n qubits or n spin 1/2, and that they are described by a certain Hamiltonian that depend on some parameter. And this is the spectrum of this Hamiltonian as a function of this parameter. Now, suppose that when the parameter is here, the system is in a very, very simple state. For example, all the spins pointing down along a certain direction. Okay, very, very easy to produce state. And that suppose now that I change, so this is in the ground state, and suppose I change the parameters slowly in time, so that the system adiabatically follow the variation of the parameter and remains in the ground state, so that when the parameter is here, the state of the system is a new state, very different from the initial one. But now suppose that I manage to encode the solution of my quantum computation into the ground state of the Hamiltonian for this value of the parameter. So in this way, with this evolution, I'm able to manipulate to deform the initial very easy to produce state into a complicated state that gives me the solution of a quantum computation. Of course, there is a caveat here. You can see that in this cartoon, I sort of hinted that there is a gap closing, and that means that when I'm passing here, I should be extremely slow to traverse this avoid level crossing. Otherwise, there will be transitions to the excited states, unwanted transitions. So in order to remain in the ground state, I should do this really, really slow. Sometimes this is called annealing, quantum annealing, for going from this initial state to the final state. Maybe when the number of spins is very large, you have a quantum phase transitions between the two phases, and therefore, as you may know, you will get a lot of excitations, a lot of defects productions during this evolution. So typically, one encodes the solution of a given problem in the ground state of this Hamiltonian H problem. It's a simple Ising Hamiltonian with certain coefficients J and H all along the Z. And because everything is here is diagonal, the eigenstates of sigma Z gives you all the energy eigenstates of HP. The ground state will be the configuration of spins up and down, 0 or 1, that give you the minimum energy for HP. So the recipe is that is to prepare the system in the ground state of this sigma X. So magnetic fields along the X. So that means the ground state is the spins down along X. So this is the state that I drawn before. And then to change in time the relative ratio between the two Hamiltonians. So if I have a gamma T here multiplying we call H driver, the driver's Hamiltonian. If I decrease adiabatically gamma of T, this is what we call the quantum annealing, and eventually this gamma of T tends to 0, the ground state of HT, so all spins down along X, will turn into the ground state of this complicated Hamiltonian, which will give us the solution of our problem. So this is a little bit the idea of quantum annealing and adiabatic quantum computation. They are quite related one to another. And this adiabatic quantum computation is applicable to a wide range of problems in optimizations, in condensed matter physics, protein folding, various satisfiability problems in computer science, optimizations, logistic problems, financial problems, etc. It's equivalent and universal. It's equivalent to gate-based quantum computing. So everything you can do with quantum computing, you can also do with the adiabatic quantum computation. And you may have heard in the news about the D-wave quantum processors. These quantum processors do use quantum annealing to find the minimum or nearly the minimum of optimization problems like this. And you know that there is all this debate about the claim of quantum advantage in these devices where they have hundreds of qubits and they perform this annealing. So what I would like to do is I would like to accelerate this annealing. And to do this, we are gonna consider a regime in which I have a low or no dissipation. This is not the regime in which the D-wave computers work nowadays. They have a lot of dissipation, but in the near future, we will get into the regime where there is low dissipation. So we are looking more in the medium term, not for the current generation of quantum computers. And we consider one of the hardest problems, which is the so-called Sherrington-Kirkpatrick spin glass from the 70s, where the Hamiltonian is the same as I've shown you before. This is a bunch of spins all interacting with each other, and where the coefficients J and H are random variables, normally distributed with 0 mean. When this is in the spin glass phase, there is an exponential proliferation of states around the ground state energy. So it's very hard to check which of the configurations is actually the minimum energy state. And this is an NP-hard problem in the sense that it is at least as hard as the hardest problem in NP, in the computational class, complexity class NP. So in order to accelerate the annealing, rather than doing this continuous decrease of gamma of T, we do a simple jump. This was inspired by this paper from last year or from 2 years ago. We do this quench where we change gamma 1 to gamma 2 instantaneously. And here you can see what you should look in this plot is the energy as a function of time. We look at this function, this red HP, which is the decrease of the energy of of the system when we do the first change in gamma 1. So, sorry, when this is the first, when we switch on this gamma 1, you see that the energy decreases a lot and then kind of thermalizes a little bit to a mean value. And then when we do the second quench, gamma 2, we reach another plateau. So we reduce again the energy and we reach some plateau. This purple line is the minimum energy that you would achieve if you were able to go to the ground state. So you see that there is still a little bit of gap between this value that we obtain and the minimum energy. This is done for 9 qubits that can be simulated classically. So we consider an alternative approach to the quench, and this is inspired by computational cooling, and this is back to collision models. So this is why collision models are still relevant for this. So we consider the following. Let's say this is the system, the spin glass, the Sherrington-Kirkpatrick model, and let's assume that there is an auxiliary system. We assume that this is a spin chain that is going to interact with with our system for a short time and then fly away, similar to the collisional model, but this is a many-body unit that is interacting with the system and then flying away for a short time. And we assume that the auxiliary system is described by a transverse field Ising model. So this is a sigma X, sigma X interaction and a sigma Z transverse field, where F is the transverse field. This model has a phase transition when F is 1/2. And then the interaction between the system and the environment is described by this Ising type interaction. Okay, so what we obtain, these are the results. This is the energy of the problem. This is the quantity that I want to minimize as a function of time for different values of the transverse field in the auxiliary system. You can see that as the different collisions happen, this is here, here, and here. These are all the collisions at these points. The energy of the system every time decreases. And then you see we let it evolve for a short time, and then we do another collision. Let it evolve for a short time, and then go on again. And you can see that we can reach very low energies compared to before. Before we reached something around -10. Here we're going to something like -15 in this unit. The other thing you can notice is that depending on F, you have different results. And you can see that the best result is obtained when F is of the order of 0.6, which is close to the critical point that you will get in the thermodynamic limit. And this is not exactly the same because this is for a small size. This is only for 9 spins. And this is also seen here for the probability to observe the ground state of the system after the procedure. So this is the overlap of the density matrix of the system with the environment. You see that the highest probability is obtained when F is 0.6. So that was the first approach that we took. The second approach, and I'm aware that my time is almost over, so I'll talk about this very briefly, is that we also measure the environment. So we do the collisions with this Ising model, and then we measure the energy of the Ising model. When we do this, we can further reduce the energy of the system. Okay, let me skip these details and show you the results. So this is done in the following way. So we make the collision of the auxiliary Ising model with your system, with the spin glass, and then we measure the energy of the environment. If we select, at each collision, we select the second lowest eigenvalue, so we see that the energy of the system is minimum. Okay, if we choose the first lowest eigenvalue, you will get worse. If you select the third one, you will get worse. If you select the second one, we find that this is the best configuration. And you can see that here now the energy of the system really gets closer and closer and closer to the actual minimum of the problem Hamiltonian. So we are getting really, really close because of this. And another result is that if you perform no selection, so this is a little bit more efficient in terms of probability, you see that also in this case, we are able to reduce, depending on delta t, on the time of the collision, we are able to reach energies very, very close to the energy of the system. Okay, and let me summarize this part as well. So I've talked about an approach inspired by quantum thermodynamics to optimize quantum annealing due to these collisions between auxiliary system and the actual system. This was inspired by computational cooling combined with our repeated collision approach. Effectively, this is using a non-Markovian bus because during the interaction there is some reconfiguration in the environment which has some memory. So effectively, we are using a non-Markovian bus. And we also shown that the measurement of the environment may further enhance the chance to finding the system's ground state. I just want to say this is work in progress. This part is a little bit rough, but I'm happy to discuss with you if you have any comment on or any question. So let me acknowledge my collaborators and you. So thank you very much for your attention.
Thank you, Gabriele. So very nice talk. So now we have some time for questions, I guess, and because I think I booked an hour or something, so should be. I mean, I hope we will not be kicked out of Zoom abruptly. So if anybody has any question, please.
Yeah, I have one, Bruno.
Yes.
If that's all right. Thank you, Gabriele, for the seminar. I think it was very insightful. On this very last part where you were showing, you know, every time the contact with the ancilla or with the external system, you manage to minimize the energy. I was wondering on the practical implementation of this, say in D-wave, right? The timescales here have, I presume this 5 units of T there is an important time scale to allow for this minimization to occur. And whether this can be practically implemented, you need somehow to cool the system or the environment every 5 steps, right? To be able to achieve something like this.
Yes, we will have to reset. The thing is that we will have to reset every time. These 5, the units is in units of, if you want, the coupling J between the qubits, okay? And every time we will have to cool down and reset the states of the auxiliary system. This is not an easy task, okay? This is challenging for the current generation of quantum computers. So I'm not saying this can be implemented tomorrow. This is much more challenging than just doing the annealing, but it's much faster. And in a sense, this can also be thought as a pre-cooling part, where in the first part of the cooling process we do this, which is very quick, and then after that one can perform some further cooling, some further annealing in the wave. Okay, so this, if you want, could be thought not as a global tool, but as even part of a procedure that involves also the quantum walk and the annealing itself. If you want to implement this in current generation, I would say this is more for IBM quantum computers, where you can, at the moment, you can actively do collisions. In the D-wave, at the moment, I don't think you can do collisions because the couplings J between the qubits are fixed, if I'm not wrong, okay? I think you can change the magnetic fields locally, but not yet the couplings between qubits which are engineered. Okay, so this is more for future generations of quantum computers, not for the current one. So this I have to be honest. Okay.
Right. Thank you.
Okay. And this method can work with smaller gaps and things like that. So is it, let's say, better?
Yes, absolutely. I mean, this is, we took a very hard problem. We didn't take any, so we took this Sherrington-Kirkpatrick with random variables, and you can see, so the energy eigenstates are known. These are all the spin up and down. So there is nothing to compute there, but it's exponential. Classically, it's exponentially hard to look at which one of them. You have to look one by one, which one has the smallest energy. So yes, there are problems of proliferations of nearly the same energy at the ground state level. And it gets worse and worse as you increase the number of spins.
Any more questions or comments? the last thing I wanted, so did you actually try the method with a simpler model? So I understand this model is very tricky and very involved, but with a simpler model, I mean, that you could really assess, I mean, exactly, you know, gaps, or that is much simpler. Because here the structure starts to be tricky. Yeah.
Yes, so these people did it for 1 qubit, for a single qubit with a Landau Zener.
Oh.
Okay, and they could show that in that case, the gap between what they could achieve and the minimum energy is smaller.
Yeah. It
So
looks
we
a
were
little
looking
bit like this bang method, you know? So there is this 2 quench, you know, something.
Yeah,
I mean,
yeah.
there is this shortcut to adiabaticity, which is called
Of course.
2 quench. Okay. Okay, very good. So if there are no further questions, I mean, thank you very much, Gabriele. I'm clapping locally.
Thank you.
Thank you.
Thank you.
Take care and see you soon. Bye-bye. Thanks everybody for attending.
Bye. Bye.
Yeah.